So today we will discuss about the UNDU-DB detectors. As we learned in the previous class that generically if I try to couple or try to use the quantum field theoretic language on background fields which are talking to atomic systems, invariably we lead into a situation where we have a Hamiltonian which is made up of operators coming from the both the sectors, atomic sector as well as the field sector. So we have seen in the previous class, we obtained in the non-relativistic settings a Hamiltonian which is made up from P dot A or A dot P kind of term, or P dot A in terms times K dot X term. In the dipole approximation, remember we expanded e to the power I kx as 1 plus K dot X. One term will just multiply with P dot A to give me P dot A kind of term, or K dot X which is appearing extra will go and combine with the whole sector. So I have two operators from the quantum atomic systems P and X, and one operator A which is coming along with the field description. Together with some manipulations we can write down this term as D dot E term as well, where D is the dipole moment of the atom and E is the electric field of the background. Similarly, if there is a spin which is talking to magnetic field, again if I do a consistency analysis, we will get up a Hamiltonian which is having an interaction term of the sort S dot B, where the S is the spin sector coming from the atomic side and B is the background magnetic field. So generically, most of the times, all the interaction terms are made up from one operator from field side, one operator from atomic side, or more operators from atomic side, one operator from field side. Typically, we avoid writing more operators from field side and one operator from atomic side because we want to discuss things in the ranges or limits where magnetic field or background fields are not very strong. So therefore, their higher powers are typically ignored or dropped off, but there is no mathematical hard and fast rule that they should be dropped. If you are interested about conditions where you have a strong electromagnetic field or strong background field of whatever sort, you should include higher order terms as well. In this course, we are just contained with the linear order, leading order coupling between the atom and the field. So I would just consider a bilinear coupling, one operator from the field side, one operator from the atomic side, just like P dot A, D dot E, S dot P, S dot B, these kind of couplings we will be more generally using. These are the lower order couplings where fields are not very strong. So we want to test the quantum properties of fields along with the matter, and those quantum properties are typically feeble to be witnessable directly. So we want to use the properties of atomic system to unravel them. Okay, and as we discussed, one very representative way of dealing with such a system is through something called the UNDU-DB detectors. UNDU-DB detector is just a representation system of this interaction, this sort of interaction. And this has most of the simplistic features which is already inbuilt in that without depending upon more subtle, no, not more qualitative or quantitative description of the field as well as the atomic system. So what we do, we think of an atomic system which has some operator, we call it monopole operator M, which talks to a background scalar field phi. So in terms of quantum field background, I'm not talking about electromagnetic field, but the scalar field phi, real scalar field. This is the most simple quantum system in the field theoretic domain we can think of. And we couple these two terms linearly, bilinearly, meaning M phi term I write down in the total Hamiltonian. The full Hamiltonian is made up of three pieces. One is the Hamiltonian of the atom, the free atom. One is the free Hamiltonian of the free field. If they are just isolated, total Hamiltonian will be the Hamiltonian of atom and Hamiltonian of the field. But since they are talking to each other, this is the coupling between them we have envisaged for M phi. Now this atom is supposed to be a two-level atom, just for simplistic consideration. We are not dealing with ideal atom, or we are not dealing with a realistic physics of quantum fields. We are just taking a representative atom with two interesting lines, excited state and a ground state. and a field which is scalar. Most of the discussion which we are going to do will be carried over to more realistic settings of P dot A, D dot E or S dot B kind of couplings without much of a issue, as we will see along. So just for a good representation, this two-level atom talking to a scalar field is a Unruh-David system, Unruh-David detector system, and through that we can anticipate what would happen for realistic settings as well. So let us go ahead with this demonstration kind of exercise, and then we will see what kind of rich physics it has to offer. All right. So now I have Hamiltonian of the system fully given like this, and then there is a quantum state of the full description. Atomic sector, as we discussed, is just a two-level system. That means I am just hypothesizing there are only two eigenstates. One is the ground state, lower energy state. One is the excited state, higher energy state. These are the two levels. Typically, hydrogen atoms or any other realistic atom will have many lines. But just for consideration, as of now, I'm just considering two. There is nothing which stops me from having more states. But just for simplification and to see the exercises with clarity, I'm just hypothesizing only there are two interesting states which I'm concerned about in the atomic sector. The field sector, I have simplified myself by going to the scalar field. I'm not going to do anything about the states of a scalar field. I will take the full spectrum of the scalar field. It has a vacuum, all the Fock basis element, single excitation momentum k0 or single momentum at excitation k1 or k2, or one excitation at k0, one excitation at k1, one excitation of k1 and one excitation in k2, two excitations of k0, and so on. So all full Fock basis is available to the scalar field. So I have an atom with two levels and a scalar field with as many Fock basis elements as it comes with. So therefore, I can start my initial state. I can prepare my initial state by taking one state from here and one state from here and just writing them as a tensor product. That would be something called a separable state. Towards the end, most likely we will be discussing about non-separable entangled kind of states if time permits. But otherwise, right now, I'm just starting my business with initial states of the kind where I have taken one state from this sector and one state from the field sector. So it could be either both the systems are in the ground state, atom is in the ground state, field is in the ground state, which is vacuum, or atom is the ground state, field is in one of the excited state, 1k0. Remember, many excited state could be there. Or the atom is in the excited state, field is in the ground state, which is excited times vacuum, or both of them are in excited states. And since fields comes with many different types of excited state, you could choose many of the possible slots to fill in the field sector. So one of the states I can take as initial state and then start my computations or analysis under perturbation theory when the system is perturbed by this term. I have ignored higher order coupling, phi square and other thing. That means I'm saying that fields are weak, the coupling is weak, and that is the perturbation Hamiltonian. If suppose this term was not there in the total Hamiltonian, then the full system will be governed by this atomic Hamiltonian and the field Hamiltonian. So atomic Hamiltonian will evolve only the states in the atomic side, and field Hamiltonian will evolve only the state in the field side. There will be nothing which will be common, meaning they will just separable. The Hamiltonian is also separable, state is also separable, so therefore their individual evolutions will also be separable. So nothing interesting will happen, only field will evolve with its own Hamiltonian, atom will evolve with its own Hamiltonian, and no coupling means they will just move along or evolve along as they do in standard quantum theory. But as soon as this term comes about, the total Hamiltonian does not remain. So any of this state, if you see any of this state, if you take, they are eigenstate of H atom plus H field. If the interaction term is not there, whatever state I am writing over here is an eigenstate of H atom plus H field system. That means under time evolution, they will remain like there. They will not evolve, only phase will be picked up. If I take one of these states, superposition, of course, would develop non-trivial phase dependency and they will not remain as they are initially proposed like. However, yet, if I take one of this separable structure, then unless this perturbation Hamiltonian comes about, they will evolve independently picking up phases. That means the state will remain there. The probability of going to any other state would be nil. So as soon as this perturbation or the coupling is turned on, these states do not remain eigenstate of the full Hamiltonian. Therefore, they will change from being this. And then we would compute under the quantization of the field and the understanding of the atomic part M, where does the state go. All right. So, in order to do this discussion, I will just recapitulate some discussions which we already had in the time-dependent perturbation theory approach, namely the Schrodinger picture versus interaction picture analysis. I will just recollect the essential things which we had already seen. So if you want to brush up, you go back to week 3 discussion or week 2 discussion where time-dependent perturbation theory, particularly the interaction picture, was discussed, and just recollecting the essential formulae from there. So remember, I have a interaction Hamiltonian, which is a perturbating Hamiltonian and is a time dependent. You see the phi field phi and M over here that we will see, both of them have a time dependence. Field changes from position to position and time to time. So therefore, this is a time dependent perturbation theory approach, where my initial state is given as one of the possibles. Let us see the state which is both the field as well as the atomic system are in the ground state, and then let us evolve the system with the full Hamiltonian. Now the full Hamiltonian, if it evolves the initial state, psi in will migrate to some new state psi f, which will be obtainable from the Schrodinger picture description through this e to the power the integration of the full Hamiltonian between the initial time to a time of interest where you want to know the system about, acting upon the initial state psi 0. This is the Schrodinger evolution. But recall, we had discussed that the same analysis can be done, the same time evolution can be understood in terms of something called interaction picture and interaction states, interaction operators, in terms of these new equations, where the timed evolved Schrodinger wave function can be written in terms of something called interaction wave function times interaction wave function, which is being acted upon by the e to the power minus I h naught t upon h bar, where h naught is just the free field part without perturbation part of the Hamiltonian. So this total Schrodinger time evolved state can be obtainable from the free Hamiltonian, unperturbed Hamiltonian's action on the something called the psi it, the interaction time evolved version. This psi I of t, that the interaction picture timed evolved wave function itself, is obtainable from some unitary time evolution operator in the interaction picture. This we all have done in the week 2 lectures, and it can be obtained from initial time evolved version, initial psi I t naught, which is again related to initial psi Schrodinger wave state with e to the power I h naught t naught, where t naught would be the time where the state was taken as the initial state. So this is how the time evolution happens. We had known previously this time evolution operator is written in terms of something called a time ordered product of time ordered exponential of Vi, interaction potential Vi, which is equivalent to Vi is equivalent to H interaction in the interaction picture for us. We will see in a minute, but just recollect, go back to your notes of week 2 rather, and recollect the formulae that time evolution of the interaction picture wave function is done through a unitary operator, which is time ordered exponential this, where Vi is obtainable from the perturbation potential V or H interaction for our case, squeezed between the unitary of free Hamiltonian e to the power I h naught t upon h bar and e to the power minus I h naught t upon h bar from the right. So this constitute for us the whole time evolution in the interaction picture. Once I know in the interaction picture where has the state landed, I can obtain through this action where is the state in the Schrodinger picture. This is as trivial. Just for completeness, let me write down the full Schrodinger time evolved state can be obtainable from the initial Schrodinger state through this exponential. time integral in the exponential, which I can write as us t comma t naught, the Schrodinger unitary. Now there is a relation between this unitary of interaction picture and Schrodinger unitary, which I have written over here. This is a simple exercise for you to prove this, that us of t naught is just interaction picture Hamiltonian squeezed between the free Hamiltonians at different times. Left hand side is unitary at time t, and this is the unitary at time t naught according to the free Hamiltonian. Again, this is nothing new which we do not know about. This is just rewriting of the formulae of week 2. Let us proceed further. In that week, we had already learned that once I am in the interaction picture, any operator's expectation value, either I can go to the Schrodinger picture analysis, take the operator, find out what is psi s of t and squeeze it between, and that will give me the expectation value of that operator. But we have learned that everything can equivalently be done in the interaction picture, where I just obtain what is psi I t's and squeeze the operator between the interaction version of the operator, which is related to the normal operator like this. This is the interaction OI. So all the expectation value can equally be computed in the interaction picture or as in the Schrodinger picture. And similarly, all the inner products as well can be computed either in the interaction picture or in the Schrodinger picture. Both of them have the same information. Okay. The benefit of going to interaction picture is that the unitary, which we had written for the interaction case, only depends on the perturbating Hamiltonian. Vi is just the perturbation Hamiltonian squeezed between the free particles Hamiltonian, free particles unitary. So ultimately, the interaction picture, the interaction Hamiltonian plays a central role, and the information captured by them are as good as the Schrodinger picture. So we will see how the Unruh-Levy detector makes use of that. Okay. So we know that in the Schrodinger picture we are initially, where the initial state, let us say, it could be, so I want to know that initial state was ground state and vacuum for the field. This was my initial state. I want to know after a time evolution, what is the likelihood that the state has become excited in the atom while field is still in the vacuum. So I am asking what is the probability that state has become this after time evolution. So what I should do, I should time evolve the initial state to psi s of t, and then take the overlap with the state of my choice that I want to know the projection on this state, E0. So this mod square will tell me what is the probability that the final state is E0. This I can compute in the Schrodinger picture as well as in the interaction picture, as we have just learned. Only thing is that I have to write down the E0 here, which was previously in the Schrodinger picture, in the interaction picture. E0's I. And remember again, any interaction wave function is related to the Schrodinger wave function through the e to the power I h naught t upon h bar. So let us just see that equation once more. Any interaction picture wave function is related to the Schrodinger picture wave function times so this e to the power minus I h naught t upon h bar can be brought onto the left hand side. So e to the power plus I h naught t upon h bar, h naught is the free Hamiltonian, acting on Schrodinger state gives me the interaction wave function. So that is the information which we have to be alert about. So here when I am writing E0 interaction in the interaction picture, this is at time t. That means it is obtainable from the Schrodinger E0 through e to the power I h naught t upon h bar. That's all. And similarly for psi st. Okay, so that mod square will give me the probability of getting a state E0 if I started from G0. G0 is the ground state for atom and vacuum for the field, and this computation would tell me what is the likelihood that the atom becomes excited, the field remains the vacuum. Similarly, we can ask a different question. What is the probability that both atom as well as the field get excited? The field gets excited at some excited state, let us say 1k. The same computation I will do, only the final state of interest will become E1k. I'm asking the probability that the final state is 1k, not 0 for the vacuum. Similarly, I could have asked another different vacuum, another different excited state for the field, E2k. I could ask this question, what is the probability that the initial state was ground state and vacuum? After a time evolution, atom has become excited and the field has become doubly occupied at a momentum k. The computation should tell me what is the likelihood. If it is 0, it should come out to be 0. If it is 1/2, the answer should be 1/2, and whatever we do. Similarly, I can ask another question, what is the probability of 1k excitation in the field sector and excitation state of the atom? Again, this projection will tell me the answer. One can further ask, what is the likelihood that the atom remains non-excited, atom remains ground and the field only excites? All these things can be obtained from psi it and taking its various projections. So therefore, in general, I can write down what is the likelihood of initial state which was G0 going to some state which is in which atom is excited while the field is in one of the possible excited or ground state. I'm writing as psi. Psi can be a mimic for either vacuum or single excitation or double excitation or triple excitation, whatever you want to put it here. And as we saw that this will be obtained from mod square of this projection. Now remember, this projection is in the interaction picture, so I have to evolve this psi it is in the interaction picture. So I will take the interaction unitary and evolve the initial psi I0. So psi I0 times acted upon by ui gives me psi I of t. That is the definition of psi I of t. Okay, and then I try to write down this is at time t while this is at time t naught. Psi I0 now has become at time t naught. So now I go back to the Schrodinger versions of that. Initial psi I0 is obtainable from e to the power I h naught t naught upon h bar acting on psi Schrodinger at time t0. In the Schrodinger picture, the initial state was g comma 0. Both the systems were in their ground state. E to the power I h naught t naught upon h bar has to act upon, because this is the definition of psi I0. So these two terms are together psi I0. Similarly, the two terms over here which are at time t now, this is the final time. These two terms are definition of E comma psi at time t in the interaction picture. Now I have converted it back into the Schrodinger picture. So you see in between I have a e to the power minus I h naught t and e to the power plus iota h naught t naught, and the interaction unitary is squeezed between them. Remember, that was your exercise. This is the Schrodinger unitary in between. Schrodinger unitary is nothing but the interaction unitary squeezed between the free Hamiltonian exponentials. Now let us use the definition of what was the interaction unitary. Interaction unitary, as we recall, was time ordered exponential of Vi. Let us go to the previous slide and see it with clarity once more, that this was the interaction unitary, time ordered of the exponential of Vi, where Vi is just the perturbation Hamiltonian is squeezed between the unitary of the free Hamiltonian. This Vi, which has appeared over here, which is the interaction picture potential. Now let us see, once this exponential has appeared over here and we have decided that the interaction potential is feeble, which is not very strong, I can see that this exponential has a character e to the power minus x, which is small with a small x. The interaction Hamiltonian is not very strong, so I can Taylor expand this exponential. So this is 1 minus x kind of term. There could also be x square plus x cube and those kind of terms, which I'm ignoring, because remember when we were discussing the linear coupling or bilinear coupling, I had already thrown higher order field operators, phi square or a square. So therefore no point containing or having higher order exponential terms here, because in the full Hamiltonian also I have thrown away the higher order terms in the field. And interaction Hamiltonian contains a field, so its higher power will contain higher powers of fields, which we do not want. So therefore, I can just Taylor expand this exponential into 1 minus this integration of this quantity. That's all. And and this would be squeezed between exponential. So this should be T naught here. This should be squeezed between e to the power minus I h naught t and e to the power plus iota h naught t naught from left and right correspondingly. So now let us open it up and try to see what do I get. I have to take this Schrodinger unitary. See, the transition probability is the Schrodinger unitary US squeezed between the Schrodinger state G0 and E psi from left and right. So I have to take this US, squeeze it between state G0 initial state and the projected final state, and mod square of that will give me probability. So let us first squeeze it between these two states of interest, and then we will do the mod square. So when I squeezed it between E psi and G0 from left and right, this E psi will go and sit on the left side, while this G0 will go and sit on the right side here. Now you will see there are two exponentials, e to the power I h naught t and e to the power minus I h naught t and e to the power plus iota h naught t naught. These operators will hit this states E psi on the left and G0 on the left. When the operator, this exponential hits the left coming bra state, which is E psi, I will get the total excited state energy of the whole system, E and psi put together. This is the free Hamiltonian, H atom plus H field, no interaction. So therefore, I will both of them here, E and psi. E is the excited state of atom and psi is one of the excited state of the field. So overall, this is the eigenstate of this operator H naught. So therefore, I will get total energy of the whole state, which I am calling E psi. E psi is not just the state energy eigenvalue of the field. It is the total energy of the whole system, E psi. Okay. Similarly, from the right hand side, when this e to the power iota h naught t naught upon h bar acts on G0, that will give me e to the power total energy in the phase, total energy of the full system E0. So I will get e to the power iota E naught t naught upon h bar. These two are just complex numbers now, pure phase. So this can be clubbed out. While these are eigenstates acting, these are the operators acting on their eigenstates, the state will come back, meaning e to the power iota h naught t upon h bar acting on E psi will give me this phase factor and the bra back, E psi bra back. And similarly, the right hand side e to the power iota h naught t naught upon h bar acting on the G0 will give me this phase factor times the G0 back. So therefore now I have this whole time ordered expansion term squeezed between E psi and G0, and outside I have a pure phase, a couple of pure phases actually, one from left side, one from right side, but pure phase after all. Now as we discussed, the probability is the mod square of such a term. So when I take the mod square, these pure phases which have accumulated outside, they get under the mod square to give me 1. So that means they do not play any active role. All I am left with is the time ordered expansion squeezed between the states of interest and mod square of that. So let us open it term by term. First term is identity. Time ordering of identity is just identity. So first term will just be overlap between the two states of interest, initial state G0 and my projection of likelihood of going to E psi. So the state of interest E psi. The second term is the first integral of VIT prime from T naught to T. Now this is a integral and single integral, and time order of single integral does not do anything. Time ordering matters only from second integral onwards. So therefore time ordered of the first two terms of the expansions are the terms themselves. So I do not have to worry about the time ordering up to lowest order perturbation theory or leading order perturbation theory. So I have two terms. Once the overlap between E psi and G0, and then iota h bar times this integral where the interaction Hamiltonian or interaction perturbation term in the interaction picture is squeezed between the two states of interest and mod square of the whole term. Now, since this E psi and G0, they are eigenstates of H naught, total free Hamiltonian of atom and field put together, they are orthogonal to each other. So that means their overlap is essentially 0. So that means I am left with only the second term's mod square, and mod square of the second term is 1 over h bar square, because iota or minus iota rather under mod square will come out as 1, and h bar will come out under mod square as h bar square, and then this integral mod square of that. Okay, so at this point we have to just recollect what was the definition of Vi. The definition of Vi was the perturbation Hamiltonian squeezed between the unitaries of the free Hamiltonian. Our perturbation Hamiltonian is M phi. Recall, in the Unruh-David detector system, I had the atomic operator M and field operator phi. So this was my V. Its interaction version will be the operator squeezed between the unitaries of the free Hamiltonian, H naught. H naught is composite of two Hamiltonians of atom and field put together. Now recall that the VIT primed, if I have to write in the interaction picture, in the interaction picture, the two exponentials come on the left and right hand side with the same time parameter T prime. In the unitary of Schrodinger and interaction, the two different exponentials come at two different times on left and right. This was just to be careful about. So I know what is my Vi of T prime. This is just the operator interaction coupling squeezed between two unitaries, and this thing has to be evaluated the matrix element has to be evaluated between E psi and G0. So I take the whole thing, this is the whole Vi for me, and squeeze it between E psi and G0. Now again, there is a couple of steps of algebra you should be alert about and see how does it get you through. As we discussed, this H naught is the free Hamiltonian of both the system, atom as well as the field. So I split it up, H atom plus H field, free part of them. And since H atom and H field are just two separable Hilbert spaces, they commute among themselves, so exponentials can be separated. So I have a e to the power I H naught of atom only and e to the power I H naught of the field only. Here I have the field only. Similarly, so let me just clean it up. So similarly, on the right hand side, e to the power minus I H naught T primed upon H bar. Again, this H naught can be broken up into H atom and H field with a minus sign at T prime. So I have a atom with a minus sign here and the field which is minus sign here. So I have just broken things apart. What do I do? Since they are commuting operators belonging to two different operators, I collect all the atomic operators on one side and all the field operators on one side. So you can just convince yourself that the whole thing over here can be written as operator M squeezed between two unitaries of atomic free Hamiltonian. And similarly, field operator squeezed between the unitaries of free field operator. They will just give you timed evolved field operators and timed evolved monopole operator of the atom, because this is U dagger on the operators. But let us not write it in that way. I just keep the atomic part as an unitary times the operator times U dagger, while the field I write it in terms of the time evolved field. This squeezing of field operator between e to the power I H naught T and e to the power minus I H naught T will just give me the phi at a future time T prime. Okay, this is just the definition of the time evolution of the operator. Here also it is time of evolution of the monopole operator M, but I am not writing it as explicitly because that helps in the next step. Because you can see here again the same game will happen. This will give me a pure phase time the state back, and while on the right hand side also you can see this term also will give me a pure phase and the state back. So I will have as a pure phase e to the power iota excited state energy coming from the left minus ground state energy coming from the right divided by h bar times t, and the operator m, which is here, that will now get squeezed between E and G. So these exponential operators convert into pure complex numbers, and the state go through them and hit the m. So you see the whole first half of this term is just this exponential times exponential of energy gap divided by h bar times t, and the monopole operators matrix element or transition element, it is called sometimes. While on the right hand side I have the field which is between the initial state, which was ground, and possibly the final state, which is psi. That is the projected state which I am looking at. So now I have the full expression for the squeezed Vi between E psi and G0. What I have to do, I have to do the mod square. I have to first do the integration and then do the mod square. Now you see here the t, actually this should be t prime because everywhere Hamiltonian was coming with t primed. So you see the phase has come with t primed, but this t prime has to undergo integration. This is not a constant t primed, it is changing t prime. So therefore all the terms which are coming in the integration do not have the same phase. They have different phases at different time. So therefore I cannot pull it as a common factor and under mod square it will become 1. That is not going to happen, unlike before. So this is a running phase. This changes at different times. So let us, better way will be, take this thing, takes its complex conjugate, because I have to first integrate it, multiply with conjugate, complex conjugate, to get the mod square. So that's what I do. I first write down the term which I have obtained, integrate it with it labeled dt prime, and then write down the complex conjugate of that. The complex conjugate of the whole term is also an integration. Only thing that this EMG will become GME this time, because M is a Hermitian operator, and the complex conjugate of this thing will just flip the role of bra and ket. The exponential will become a minus sign over here, and again the flipping between psi and 0, because the scalar field also is a Hermitian operator. Now I am settled. Now I have the full probability of transition. So therefore, now I can see this EMG, whose complex conjugate is GME, is time independent. Remember, this was M0, which was getting squeezed. This is not a time dependent function. All the time dependency was captured in the exponentials. So this is time independent. So therefore, these two terms can go out of the integral. So outside I will get a mod square, because they are complex conjugates of each other. I will get a mod square. Inside I will be left with dt primed integration, and you see now there is a relative time difference which appears in the phase, because these phases were running phases at each integral different time. Two such terms have to be multiplied, so therefore exponentials will have a relative phase with a relative time difference of running times. What I have done in the next step, I have called t primed as t and t double primed as t prime. This is just for simplification of notations. All of them are running variable. You could call it x and y. Here also x and y. You will see both the terms are equivalent to each other. Only thing you have to be careful about, that now this is a complex number. A real field or Hermitian field squeezed between two different states can give me a complex number. So these are not operators anymore. They are just matrix elements or complex numbers. So I can flip them. So I can first write phi t double primed between 0 and psi, and then psi phi t prime between then psi phi t primed at 0. So I have flipped this complex number, because complex number can be flipped, operators cannot. And you remember t double primed was being called t primed in the next step, and t primed was being called as a t in the next step. So you see the exponential, which was t primed minus t double primed, can be written as t minus t prime, and the operator which is coming first is phi t double prime, which has become phi t prime, and later I had written as phi t prime, which has become phi t. So this is like this. Okay, so this is somewhat of a neatly looking form. Now suppose we are interested only in knowing what is the probability of excitation of atom irrespective of whatever happens to the field. That means I am not interested about where the field goes. Let it go to any of the Fock bases. I do not care. That means I should ask for all the possible processes, add up their probabilities where atom gets excited. That means 0 to E, but field goes to 0 to 0 or 0 to 1k or 0 to 2k, 0 to 1k, 1k not, and all such possibility of psi. That means psi of the all Fock bases I'm going to add over all the probabilities in which the first part gets excited, second goes wherever it likes. So all the final states I sum over. If I do that, if I ask this limited question that I do not care what happens to the field, I just care about what happens to the atom, you will see that this summation of the probability, this psi which is being summed over, will go and sit here. You see there is outer product psi coming in the previous step. So this summation over psi will go and sit over the outer product of psi. Remember, psi was a Fock basis element, one of the Fock basis element, whichever you like. And now I'm summing over all Fock basis elements. That means it's a outer product of all basis elements, and this constitutes an identity in the field space. So therefore, I am left with, if I just want to ask this limited question, what is the probability of atoms excitation? Then that limited question gets answered by this exponential, the integral, double integral, this exponential. See here also in the exponential I have done a funny way that I am writing t minus t prime as a minus of t prime minus t. This is just algebraic manipulation, nothing serious. But in the interior, the operators which are sitting inside is phi at t primed, identity, then phi at t squeezed between 0 0, vacuum of the field, where the field started with. Where it lands up I do not care, but I know where it started with. It started with the vacuum, and then this identity does not do any active role. So phi t primed identity phi t is equivalent to phi t primed phi t. Now I again relabel. So t primed appears first in the exponential with a minus sign, and phi t primed appears here. T appears in the argument of exponential at the later stage, and the t here appears second. That means whatever is the argument of the second field is the later argument of the exponential, and whatever appears in the argument of the first field is the first argument of the exponential, which means I can just call it x and y again. T primed and t can be flipped in the sense of I can relabel whatever was t primed, I can call it t, and whatever was t, I can call it t primed. This is just integration variable change. Under that you can see that this just becomes e to the power minus of iota t minus t prime, because I'm going to call t primed as t and t as t primed. Phi at t prime becomes phi t, and phi at t becomes phi t prime. So you see, this is the correlator of phi at time t and phi at time t primed, which has appeared. When I summed over all the possible states of Fock basis where the field can land up, I end up getting the 2-point correlator of the field at time t and time t primed. And this t and t primes are running from initial time t naught to final time t. The probability of transition collects the information of the 2-point correlation function and does this some sort of a double Fourier transform. It looks like a Fourier transform by structure. We will see what it is in the next class, but you see the structure. The 2-point correlator comes in the game, and that tells you what is the probability of transition. 2-point correlator at time t and time t primed at the locations of the atom. So atom is at time t at some location, at some other time t primed it has moved to some other location, and the field values there, how much they are correlated, that tells us what is the transition probability. So that is why we are calculating the field correlators in the previous classes. Now we see that the field correlators decide the transition probability between different states, and therefore they are useful quantities, not useless. See, we started in vacuum state. Field expectation in vacuum, as we know now, is 0. So there is no active photon expectation value wise in the field, but vacuum has a quantum fluctuation. That quantum fluctuation is captured by this 2-point correlator in the vacuum state. Had it been a classical state, if there was no classical field, there will be no 2-point correlator as well. That would be 0 as well, and no probability of transition. But this time Despite its expectation being zero in the vacuum state, the correlator is non-zero. That is a quantum feature, and that correlator's double Fourier transform of this kind will tell me what is the probability of the atom's excitation. So therefore, we will need to compute this 2-point correlator at T and T prime, which we have done already. So I will just use that result in the next class and show you what is the probability of transitions of atoms at excitations, de-excitations, and other things of atom through quantum fluctuations. This is not a classical field anymore. This is quantum field, and quantum field's 2-point correlator function is deciding us for us what is the transition probability. So in the next class, we will see what is the transition probabilities with the usage of these correlation functions. And now we will see the quantumness of fields have started mattering when I couple quantum field to quantum matter. So I stop here for today. In the next class, we will see the transition probabilities.